Thank you very much for your kind words to introduce me. It's a great pleasure to be here today. As we all are noticing, the world is changing, and I think the speed of change is faster and faster. Not only in Asia and China, where we see tremendous speed in everything happening. And I'm afraid, as you all are all aware, all the changes happening are not that beneficial. And what we see in the public health side is that actually the entire world is getting obese. And again, here, Asia is unfortunately following what is happening in Europe and in the US. CVD, type 2 diabetes, metabolic diseases that are linked with obesity, then cause that everywhere in the world the healthcare costs are rising, and rising too fast to maintain the level of healthcare that we are having currently. And still, according to the American Heart Association, heart disease and stroke still are the leading causes of morbidity, mortality, and the costs all over the place currently. As the theme of this seminar today, many people have started to tackle these diseases, getting more understanding of the etiology, with the hope that we could develop better prediction models, particularly for the primary prevention. And this is what our team does with omics profiling. I'm going to introduce a little bit from the scientific side. What does it mean? What is our metabolomics platform that we have developed? How it can be applied in epidemiology? What's the advantage of applying? And then at the end of the talk, a few words how these new technologies might enter and help the public health problems, and a little bit, at least, our vision how the future medicine could be shaped. I will show a very recent example of our own work. Looking at blood from the medical perspective is maybe the most standardized thing in global medicine. It comes quite naturally to look at biomarkers and cells in the circulation, because on one hand, these biomarkers that are in touch with all the various tissues of our system may tell something about what is happening in the various tissues. And on the other hand, the circulating metabolites can also affect how the various tissues function. So to be able to treat people better, to be able to save society's money, we should be able to pinpoint those individuals from the population that are at the highest risk to get these diseases in the future. 50 years ago, actually Finland was in the questionable pole position, having the greatest CVD mortality rate in the whole world. That was 50 years ago. It's not anymore. And actually 50 years ago the government took serious actions and set up this North Karelia project in the eastern parts of Finland, where we have the beautiful lakes and beautiful nature. But the people were in big danger of CVD. So this actually eventually, the project spread throughout the country. And what happened, there were actually, and I mean now if I say that let's have a media campaign, it's no big deal. But 50 years ago, what the government did, it did a media campaign that you should exercise more, you should eat better, you should use less butter, and you are not supposed to smoke. And I mean all these factors still big controllers of public health. But in 25 years from the start of the program, cholesterol levels came significantly down around 30%. Other risk factors, using butter, smoking, increasing physical activity, and all that in total resulted that in 25 years the CVD mortality came down more than 70%. This is a brilliant example how we can affect whole nation via epidemiology, via population-based medicine. This study actually became world famous for its results. And I mean, one of the key reasons was that a causal risk factor for coronary heart disease, cholesterol, came down. So obviously it's easy to understand that the outcome prevalence also came down. However, when digging deeper and looking at the etiology of CVD, even though the population medicine and statistics works, you still can't say anything at an individual level. So as an example, roughly half the people who are hospitalized with heart attack have a normal cholesterol level. So the predictive value at an individual level is very low. And that's kind of means that if we are looking at here the bad cholesterol, the LDL cholesterol population distribution, it is very difficult to draw this line above which you are at higher risk. So we still have a lot to learn. There are still many other factors, there are many other biomarkers to be found that control the process of atherosclerosis. And here, the recent 5 to 10 years has been a beautiful rise of various omics technologies. First with genetics, and then following like metabolomics, what our field does. And it has clearly already provided a lot of etiological understanding of various metabolic diseases. What I will tell you soon is that actually applying these kind of metabolomics technologies, we can bring down the cost of doing better science. Whether these savings and these kind of etiological understandings go to public health and what's the time needed for the translation, I leave it to your consideration at the end of the talk. Our belief is that these technologies will really help also bring down the costs in the public health sector. What we have developed in our team in the last 10 years or so is an NMR-based serum metabolomics platform, which actually nowadays is more like an industrial, fully automated process than anything to do with the typical chemical NMR spectroscopy that you are aware from your chemist colleagues. So we can receive samples from all over the world. The key issue is that they are, for a long time, storage needs to be at -80. During the transportation, they need to get frozen. When they enter our lab, they enter in a fully automated process with the QC automated pipetting robots, and then eventually making these samples to animals suitable, and then all this is automated. And actually the most of the work in developing this automated methodology from my team has come to the automated database. And that took over 5 years to really have well operating, and now we have spent 10 years in that, and now it really is. I know that some IT people in the audience will not believe if I say that it's a push button, everything works, but it is. And we are now implementing it in the NMR spectrometers as well. So immediately you measure the sample, you get the biochemical concentration. About the metabolites, we quantify something like 250 metabolic measures. Contains a lot of various cholesterol measures, triglycerides, phospholipids, fluid balance. Currently 9 amino acids, it's going to be 14 when the platform is finalized. Ketone bodies, glycolysis related to metabolites, a very interesting inflammation marker, and a bunch of fatty acids like omega-3, omega-6, polyunsaturated fatty acids. And a very extensive pattern of lipoprotein subclass information concerning 14 different lipoprotein subclasses. We have now used this platform to analyze around 350,000 samples in a bit less than 7 years. And these samples came from over 100 individual epidemiological and clinical studies. We have actually found new biomarkers for various conditions. For early atherosclerosis, meaning the carotid INT, and more recently also the CVD endpoints. We have rather extensively looked at type 2 diabetes and also diabetic nephropathy in type 1 diabetes patients, all cause and specific cause mortality as well. We have now published almost 100 papers on the development and application of this particular platform over the last 10 years. So this particular platform, the findings, how it relates to the conventional clinical chemistry, how it relates to the outcome prediction, is pretty much established in a ground level currently. We recently published a review opinion on this, and then generally what is happening in the field of quantitative serum metabolomics. The key point to pinpoint here is that please note, when applying this platform, you will actually get a big bunch of routine clinical measures as well. And I will actually show you soon that if you would measure all these individually with traditional clinical chemistry, you would end up paying more money for these rather than having the entire metabolomics platform. So that is one issue that, as I said, in science, these kind of technologies will allow you with less money to do better science. And this technology is available now. This is our lab in Bristol, 2 of these NMR machines and the automated robotic hand and storage system. These 2 machines, the annual throughput for the serum analysis is a little over 100,000 samples. We currently have 5 machines up and running in Finland, and early next year we're going to have 5 in the UK. So this is not football. If it were football, it wouldn't be this big. But if it were ice hockey, it would be the other way around than with football. And we have also set up a company, and through the company we are able to make this platform and this methodology available to everybody that would like to run their samples for a very attractive cost structure. So early next year, when we have also the Oxford and the UCL machine up and running in the UK, the total capacity, annual capacity, is about 500,000 samples. So we start to match for the big cohorts for how fast the genome-wide analysis can be run and so on. And let's look at the cost a little bit. The genome-wide data, to acquire that would cost something like 3 times the cost of this NMR-based metabolomics data. if we would look at the comparable mass spec, it would be 10 times more expensive. If you would take the best in mass spec currently available, meaning 6 to 700 quantified tablets, you would need to pay 30 times more than for this particular platform. And depending on the sample volume and the number of samples, the price for this platform is somewhere around 15 to 25 euros per sample. And now you realize that it's not that many clinical chemistry measures that you separately analyze and pay that comes to 15 euros. So let's have a recent example that we looked at regarding the data from this particular platform and predicting CVD event risk later in time. It was published in Circulation early this year, and we looked at in total in 3 population-based cohorts, 13,500 individuals with almost 2,000 outcomes. And now we come to an interesting issue. Amino acids have been known for quite a long time. And LDL cholesterol is a well-known causal risk factor for CVD outcomes. And if we look at the risk predictive ability of one of the amino acids, phenylalanine, it actually came out a lot stronger than LDL cholesterol. So there seems to be something interesting related to the etiology of CVD that is not captured by the LDL cholesterol. In general, the metabolites that we looked at, we found 33 measures actually associated with incident CVD events. And let's not go into the detail, let's see a little bit. The apolipoprotein measures, the ApoB and the cholesterol measures, so these are from the metabolomics platform. And these results are known from the clinical chemistry, but the result is exactly the same as it's supposed to be. This is just to confirm that what we see through this platform is giving the expected biomarker. And then for the HDL and ApoA1 appears to be a predictive biomarker. And then we come to the new findings, phenylalanine, and actually another amino acid, tyrosine, which is at the level of same predictive ability as LDL cholesterol. And then we go to the future development issues. If we look at this new biomarker, phenylalanine, we look at trying to predict death from coronary heart disease, it's a good risk marker. However, if we look at stroke, it's not a predictor at all. So this pinpoints that to improve the prediction models, we would really go for the stratification of the outcome. It's not enough to talk about CVD. We have to go more accurate definition of the clinical outcome. And then if we look at the same new biomarker for CVD risk in different population groups, we actually see that it's a good biomarker for younger individuals. It has no predictive ability in older individuals. So, meaning that the stratification needs to be taken to the people as well. So we need to stratify the population. So, in our team now, the main job regarding CVD risk prediction is to construct this kind of fruit machine. We have the population characteristics here, whole population, different age groups, people that are obese, men, women, those with or without type 2 diabetes. It's rather endless number of different clinically relevant categories. And then we have the different clinical endpoints that we also need to stratify. And then we have the bunch of 200-300 metabolic measures. So I mean, this is a challenge. And that is actually one reason why we developed what we developed. cost-effective, high-throughput metabolomics platform. Our thinking is that we start to have a base once we have analyzed million individuals. And to hit the jackpot, we actually think that maybe even 10 million individuals that we need to have the stratified models to improve primary prevention. But we believe that this is a goal worth pursuing, and it will clearly improve the modeling and the primary risk for CVD. And then towards the end of the talk, let's add genetics to the multi-omics picture. Because we have been able to measure so many samples, we have actually been leading the genome-wide metabolomics field. It was almost 4 years ago when we published the first genome-wide metabolomics paper. And it was actually less than 10,000 individuals. But we found 11 novel loci that are kind of behind explaining the systemic metabolism. Now, if the reviewers are finally beneficial, we'll get the second round of this published tool, and now we have been looking at 25,000 individuals. We will start round 3 for this genetic background for systemic metabolism, and at that point, this number is expected to be over 150,000 individuals. And we'll then also incorporate the first people with Chinese ancestry. It's obviously important to understand the genes that control systemic metabolism. However, in our opinion, it's even more intriguing to combine metabolomics and genetics for the biological understanding. And I just saw a quick example from our paper a few years back relating to the lipoprotein metabolism. So if we were looking at genetics and lipids without metabolomics, the result is on the screen. So we have the genes that associate with cholesterol. That's it. That's your final result. If we add the extensive lipoprotein data from the metabolomics platform, the result is this, and we really can start looking at individual genes and how they control which phase of the continuous lipoprotein metabolism. And some genes we start to understand behave very differently than some others. So really, through the combination of genetics and metabolomics, we are a lot further in the functional understanding how a biological system works. And my last example to conclude, and a few words about future. It's obviously predicting the future is complicated, but I'm trying to say a few words anyway. In our opinion, in future medicine, these all will come together. So we will do it in large scale. We will combine various omics platforms, and we do it together with longitudinal follow-up of the individuals, which most likely happens through the electronic health records. And I was lucky regarding this presentation because our recent paper actually putting all these together, luckily, came out on Thursday in Cell Systems. And this is a daughter journal for Cell. And it actually puts, regarding one single biomarker, it puts all these things together, and I'll explain a little bit more. 2 years ago, we published this paper. We found a few biomarkers that predicted all-cause mortality over 5 years. This glycoprotein acetylation was one of the biomarkers. So we we focused all the effort to that particular biomarker and went on. We aim to really characterize why is this particular molecular group predicting death. What are the biological mechanisms behind? We had over 10,000 individuals, and we also had a 14-year follow-up through the electronic health records. We did a lot more analytical work. We did an extensive cytokine panel that we associated with this new biomarker. We did genetics, and we also did gene expression studies. And we did gene expression in 2 different population cohorts, so that we could replicate also the gene expression, not to rely on a single cohort. We know that gene expression is a tricky experimentation, so we wanted to be sure that it replicates. And it actually, here you see the replication of the gene expression. It replicates really well. And what we actually were able to put together was a gene expression family that related to neutrophil activity, saying that those individuals with high levels of this biomarker are likely to have chronic inflammatory response. 27 different genes that then we were able to relate to the molecular biology and biological processes. Then we looked at the electronic health records, and it actually turned out that this particular biomarker really predicts death from infectious diseases over almost 40 years of time. When we dig deeper the electronic health records, and more specific disease categorizations, we see that for multiple, let's say, respiratory infections, this particular biomarker shows risk for both hospitalization and mortality for various infectious diseases. So we believe that this is a kind of example how when we find new biomarkers, what we should do, not to be particularly happy about the first finding, but to dig deeper, go to the mechanisms, really show the biological relevance, and then try to link if this particular biomarker would have relevance in the clinical scene. So in this particular case, and I think this in the literature is one of the first, if not the first, going through first the finding in a separate paper and then the extensive biochemical explanation. And I think we are pretty close to translational opportunities regarding this biomarker. And concluding, something for you to trying to remember of all these omics when you go home. Large numbers are the ones we need. Try to do as large studies as possible. Try to replicate, even if you have large numbers. Try to replicate. And from a personal perspective, I would so much welcome collaboration with Asia, because the majority of the 350,000 samples analyzed we have are Europeans. And we know that, for example, for type 2 diabetes, the Asian ancestry gives you twice or 3 times higher risk. So very interesting to put these together, and very much welcome collaboration. If you can afford, and at some point I think we are, the more genetics we can have in an epidemiological study, the better we are off in explaining the functional issue and understand the processes themselves. But this is maybe not within the next 2 years, but maybe takes 5 years or more time to have extensive studies like this. And then the electronic health records, longitudinal follow-up of the individual. It's a lot more powerful than doing cross-sectional studies only. And we all need to remain physically active. Thank you very much for your attention.